In this video, we're going to prove that if the greatest common divisor of a and b is 1, then the greatest common divisor of a raised to the n and b raised to the n is 1 for every positive integer n. So to prove this, we are going to use strong induction. So what is the strong induction? So briefly, you need to have a statement Pn, which is a statement with positive integer n. And the first thing you have to do is to show that P1 is true, which is called base step. Okay, so once you have P1 is true, you have proved the base step. The next step that you need to prove is to prove that P of k is true for every positive integer k, such that k is greater than or equal to m. And what is m? M is an integer that you have to assign. And then you have to show that Pm is true. So once you show this step, you prove that the inductive step is true. Okay, so once you prove all of these steps, you prove the statement with Pn. Now, let's take a look. Let's start to prove this problem. So we have to start with proof. And we will use the strong induction. Actually, it is the second principle of mathematical induction. So we need to use a proof. But the first thing you have to do, I think we have to assign the value of a and b. So a and b are integers, such that when it comes to greatest common divisor, a and b cannot be 0 at the same time. Okay, so a is not 0 or b is not 0. And then we assume that the greatest common divisor of a and b is 1. And then we will use the strong induction, or the second principle of mathematical induction, to prove. I gotta say this theorem. Okay, and we will let P of n be this statement: b a to the n b to the n equal 1. Okay, what next? Let's go to the base step. Okay, let's go to base step. For the base step, what do we have? So for the base step, we need to start with the case where n is 1. Okay, so by the assumption, for the base step, you're gonna prove it. Okay, you will prove it easily because when n is 1, you're gonna have a to the 1 and b to the 1, and the greatest common divisor of a and b will be 1, which is the greatest common divisor of a and b, which is 1. Hence, P of 1 is true. Okay, P of 1 is true. So we already have the base step. But if you're not so sure, let's try to plug in n equal to 2. That means that I have to show that. Try to show that a square, the greatest common divisor of a square and b square, equals 1. Okay, let's get started. So we have to start with this assumption, which is the greatest common divisor of a and b is 1. Okay, this one right here. So once we have the greatest common divisor of a and b being 1, what do we have? So do not forget that according to theorem 2.4.3, what do we have? we're gonna have the greatest common divisor of a and b equal 1 if and only if there exist integers x and y such that the greatest common divisor of a and b equal ax plus by. Okay, this is theorem 2.4.3. Now, since we have the greatest common divisor of a, b being 1, we can use theorem 2.4.3. So what do we have? Theorem 2.4.3 implies that there exists x and y being integers such that ax plus by equals 1. Okay. Now once we have this one, we need to try to have the greatest common divisor of a square and b square being 1. So I might start with ax. So from this equation, ax becomes 1 minus by. And square both sides, we're going to have a square x square equal to ax square, which is 1 minus by square, which is 1 minus 2by plus b square y square. Okay, now we have a square and b square. Okay, so let's rewrite this equation again so that we're gonna have one side is in terms of b and one side is in terms of a. So we're gonna have 2by minus b square y square equal 1 minus a square x square. And I will factorize this left hand side. I will factorize this by by. So factorize by, so we're gonna have 2 minus by, so it becomes by equal 1 minus a square x square. And square both sides, we're gonna have 2 minus by square b square y square equal 1 minus a square x square square. Okay, now what happened to the right side, the right hand side? So the left hand side remain the same. Okay, now what happened to the right hand side? We distribute square both sides. Okay, or we expand this term, so we're gonna have 1 minus a 2a square x square plus a to the fourth x to the fourth. Then we have this number 1 right here, and we already have b square right here, and these two terms will have a square as a factor. I think we might have the greatest common divisor of a square and b square being 1 soon. Now let's move this one to the left side. We're gonna have 2a square x square minus a square x to the fourth plus what? 2 minus by square b square b square y square equal 1. And factorize this term. We're gonna factorize a square. We're gonna have a square times 2x square minus this should be a to the fourth. Okay, so we're gonna have a square 2ax square minus a square x to the fourth, okay, plus b square times 2by square y square equals 1. And it's obvious that these are integers. Okay, so since this term 2x square minus a square x to the fourth and 2 minus by square times y square, these are integers. So if these are integers, we're gonna have a square times integer plus b square times integers equals 1. Then what do we have? So and we have this equation, right? So we're gonna use this theorem, okay? Oh, I forget to write equal 1. I forget to write equal 1. So actually I write this theorem wrong. So if you have the greatest common divisor of a and b equals 1, then there exists integers x and y such that ax plus by equals 1. So from this right here, we have a squared times integer plus b squared times integers equals 1. So theorem 2.4.3. Theorem 2.4.3 implies that. So what does it imply? It implies that the greatest common divisor of a squared and b squared equals 1. Okay, so once we have this one right here, P2 will be true, right? Okay, hence P2 is true. Okay, P2 is true. So now we have P1 is true and P3 is P2 is true. Okay, P1 is true and P2 is true. I think I'm gonna try to show that P3, P4, P5, P6, and so on are all true. So we'll end this base step right here. Let's go to inductive step. Let's go to inductive step. So what is inductive step? For inductive step, we gotta assume that. We assume that P of K is true. Is true for all, okay, for all integers K, right? Such that K less than M. Okay, less than M. And M must be greater than or equal to 3. Okay, it's like we have P of K is true for K less than M and M greater than or equal to 3, right? That means that if you can prove that, so we have to try to show that P of M is true. Okay? So now, if we can show that P of M is true, we can show that P of M, where M is greater than or equal to 3, are all true. That means that P of M, P of 3, P of 4, P of 5, P of 6, and all the way and so on are all true. And P of K, in the case where K is less than 3, are all true because of this assumption. Okay. Now, let's continue. So we assume that P of K is true. What happened? Okay. Since P of K is true, what do we have? It's true for all. It's true for all positive integer. It's true for all integer K, right? Such that K less than M and M greater than or equal to 3. What do we have? So we gotta have the greatest common divisor of A to the M minus 1 and B to the M minus 1 equal 1, right? Okay, because M minus 1 is less than M. Okay, M minus 1 less than M is satisfy this assumption. So we have this greatest common divisor being 1. And once we have this greatest common divisor being 1, so what do we have? So by theorem 2.4.3, what does it imply? It implies that there exists, right? Let's use x1, y1, there exists integers x1, y1 such that a to the m minus 1 x1 plus b to the m minus 1 y1 equal 1. Okay, so once we have this equation, let's try to have a to the m and b to the m equal 1. Let's try to have this greatest common divisor. I think we need to have one terms of a and one terms of b. So we need to have that thing. So we have to take a look at this assumption right here. I think this one might be useful. So once we have greatest common divisor of a and b being 1, what do we have? So since the greatest common divisor of a and b is 1, so theorem 2.4.3 implies that. So what does it imply? It implies that there exists integers x and y such that ax plus by equal 1. Okay, then what do we have? So we gotta have, let's write ax plus by times this term. Okay, a to the m minus 1 x1 plus b raised to the m minus 1 y1. And then take a look at this carefully here. So if you multiply this term, what happened? Okay, you will have a to the m, right? And b to the m. Okay. And what about ax times this term? In this case, we're going to have a to the m minus 1. But what we need to have is to have a to the m and b to the m as a factor. Okay, so now what happened is we do not have enough degree of a and b. So you need to try to have more degree by raised to the power of 2. Okay, to make sure that the degree of a and b is enough so that you can factorize a to the m and b to the m. Okay, so you're gonna have 1 times 1 square and it turns out to be 1. Okay, so if you're not so sure, you might multiply these two terms. So what do we have here? Then you're gonna have, okay, let's expand this term. You're gonna have a to the m x1, right, plus a to the b to the m minus 1 xy1 and by times these two terms. So you're gonna have a to the m minus 1 y x1. I forget b. Okay, I forget b. So this is b plus b to the m y1. Okay, so this term have a to the m, but the next term, this term right here, did not have a or b raised to the power of m as a factor. This term does not have a to the n and b to the m as a factor, and the last one have b to the m. Okay, so I have to write square right here in order to have enough degree of a and m. Okay, now let's factorize. Sorry, let's expand. So we're gonna have ax plus by. Now what happened to this one right here? We're gonna have a and 2m minus 2x1 square, right? And plus am1 b raised to the m minus 1 x1 y1 plus b 2m minus 2 y1 square equal 1. Okay, what next? Distribute ax into each term. Okay, so I'm going to have this. We're gonna have Okay, let's distribute term by term. So we're gonna have a to m minus 1 x x1 square and 2 m to a to the m b to the m minus 1 x x1 y 1 and a b to b raised to the 2m minus 2 x y 1 square, and then distribute b into each term. So we gonna have a to the 2m minus 2b y x1 square plus 2a to the m minus 1 b to the m y x1 y 1 plus b to the 2m minus 1 y 1 square, okay, equal 1. Okay, what can we do next? So take a look at each term. This term have a to the m as a factor. This term also have a to the m as a factor. This term has b to the m as a factor. This term has a to the m as a factor. This term have b to the m as a factor, and this term have b to the m as a factor. So we group this term, right? So I gotta write this one right here, this one here, this one right here, okay, and this term, and this term, okay. So we will group this term. So I will let the terms with the factor of a to the m be next to each other. So we're gonna have a to the 2m minus 1 x x1 square plus 2 a to the m b to the m minus 1 x x1 y 1 plus a to the 2m minus 2, okay, b y x1 square, and plus a b to the 2m minus 2 x y1 square plus 2a to the m minus 1 b to the m y x1 y1 plus b to the 2m minus 1 y y1 square equal 1. Okay, then factorize a to the m. So what do we have here? We're going to have a to the m times a to the m minus 1 x x1 square plus 2 b m to the 1 x x1 y1 plus a to the m minus 2 b y x1 square. This is for the first term. We factorize a to the power of m. Next term, we factorize b to the power of m. So we can have b to the m times a b m minus 2 x y1 square plus 2a to the m minus 1 y x1 y1 plus b to the m minus 1 y y1 square equal 1. Okay, that was exhausting, right? So we have a to the m here and b to the m here, and the sum of integers is an integers, right? Okay, these are integers. Okay, so now we will use theorem 2.4.3, which is this one right here. Okay, so now let's continue. So I have to add one more page. So take a look at this one. I gotta give this reason. So since this term and this term right here are integers, okay, since this term are integers and this term is 1, a to the m times this integer, okay, and b to the m times this integer. So these are all integer, okay. So what do we have? So we can use theorem 2.4.3. What does it imply? It implies that the greatest common divisor of a to the m and b to the m is 1. Okay, that means that p of m is true and m is greater than or equal to 3. So we have proved the inductive step already. Okay, so therefore by the strong induction, okay, we have proved that if the greatest common divisor of a and b is 1, then the greatest common divisor of a to the n and b to the n is 1 for all positive integer n. Okay, and this is the proof of this problem. We use the strong induction to prove this problem already, and that's it for today, and that's it for this video.